Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the first part of Chapter 9, the penalty method and augmented Lagrange method. This chapter is divided into the following parts. First, we will introduce the quadratic penalty method and then the exact penalty method. Finally, we will introduce the augmented Lagrange method. If we have time, then we will discuss more properties and applications for the three types of method. Now, we begin with the first part of this chapter, the quadratic penalty methods. Let's take a look at the equality constraint case first. So we try to minimize a function value f about x, and we have some equality constraints only, right? And in this case, the idea of penalty method is that we try to put the constraints into the objective function and we transfer it into an unconstrained problem. So if we put the constraints into the objective function, then we cannot guarantee that x may satisfy the constraints. Therefore, we need a measure to penalize the violation of constraints. Okay, so the quadratic penalty function or the quadratic penalty methods basically means that we take the quadratic penalty term of the constraint into the objective function, right? Now, the quadratic penalty function for the problem here is that we just penalize each of the equality constraints into the objective function and we take the quadratic term. After that, we make the sum of all the violations and then we multiply it by a penalty parameter mu. Okay, so this will form the quadratic penalty function. In other words, if we solve this quadratic penalty problem, then we may reach a function value. However, this solution may violate the constraints here. Okay? So suppose or assume that we drive the penalty parameter mu to be infinity, then we can actually see that we will restrict the feasible solution to be in the feasible sets here. Okay, so this is the idea of quadratic penalty method. Now, we have several remarks about the quadratic penalty method. The first one is, as I just mentioned before, if we drive mu to be positive infinity, we can actually restrict the set, or we can actually restrict the variable inside of the feasible region. Okay, so this is an infinity case. And this motivates us to consider a sequence of the penalty parameter mu that we move gradually to the infinity for this penalty parameter. Okay, so a question is that can we initially set this mu to be infinity? The answer is that we can do this. However, in this case, this problem may be in a very bad condition number. So we have to set this mu from a very small value and then we increase it gradually to solve a sequence of the penalized problem. All right, so for each mu k, after we fix mu k, then we got an unconstrained problem. So we solve this unconstrained problem to get an approximate solution, right, which may violate the constraints. And then this solution from the quadratic penalty problem can provide us the initial guess to solve the next iteration. Okay? By doing this, we hope that the limit point of the sequence will converge to the optimal solution of the original problem. Now, for solving the unconstrained problem inside of the out loop, we can use just a few iteration steps to reach an approximate solution. Okay, so we do not need to solve the unconstrained problem exactly to the optimal solution. We just solve them using a few steps. That's enough. Now, let's show you an example how the quadratic penalty method works. So we have the examples, which is the same as in chapter 7. We minimize the sum of two components and subject to an equality constraints here. This equality constraint is basically a circle with center origin, okay? And the quadratic penalty function is like this. So we take the quadratic term of the constraints and we multiply it by a quadratic penalty parameter mu. Then by doing this, we can get the quadratic penalty function qx mu. Now, let's take a look at the figure where this qx mu lies. Now, this is a contours of the quadratic penalty function. As we can see that the minimizer is actually achieved at this point, minus 1.1, minus 1.1. And near x equals dot 3, we actually got a local minimizer here, right? So this is a local minimizer. So it actually means that by setting different parameters, we may got different contours of function values, which may return us different minimizers. Now, if we set the penalty parameter mu is dot 1, then we can get a function value contours like this. Okay, so you can see that the contour shape is similar. However, they do have different local minimizers and global minimizers. All right. Now, another question is that for inequality constraints, what can we do, or what kind of quadratic penalty function can we use? Okay, so the inequality constraints basically means that if we got feasible solutions Cix greater than or equal to 0, then we will not penalize the problem. Okay, if it is smaller than 0, then we need some penalty. Therefore, we add an extra penalty term here, which means that if Cix is smaller than 0, then we take the max of 0 and minus Cix, then this will be a positive part, okay? And we take the square of this part, then this will make the quadratic penalty term for inequality constraint case, okay? So putting together the equality penalty term and inequality penalty term, then we get the quadratic penalty function for both equality constraints and inequality constraints. And notice here that the penalty parameter mu, they are the same, okay, for equality 1 and inequality 1, all right? So for general problems, this will be the quadratic penalty function we can use. After that, we are now ready to give the outline of quadratic penalty method. So before that, we have some settings. So the starting penalty parameter mu0 and the sequence tau k, which controls the tolerance of solving subproblem. We assume that tau k goes down to be 0 and the starting point xs0 for the very starting point of first loop. Then we start the loop in the following. So we first find an approximate minimizer xk of the quadratic penalty function with the starting point at xsk. Then we stop solving the inner problem or the inner unconstrained problem until the first order optimality condition approximately holds. Okay, so this norm of the quadratic penalty function greater than or equal to tau k basically means that xk is an approximate first order solution for the problem. Now we check whether we can stop. If the final convergence test is satisfied, then we stop. Otherwise, we can choose a new parameter which is greater than the original penalty parameter. Then we solve the problem again with the starting point x as k plus 1. Okay? In other words, the quadratic penalty method actually transfers the constraint problem to a series of unconstrained problems, which we increase the penalty parameter gradually, and hopefully the limit will be the optimal solution of the original problem. Now, in terms of the convergence of quadratic penalty method, we have two theorems. The first one is about the global minimizer result. Okay, so we assume that each xk is the exact global minimization of quadratic penalty problem. Then we can show that every limit point x star of the sequence xk is a global solution of the original problem. In other words, if for each inner problem we can get the exact global minimizer xk, then the limit point of xk by driving mu k to be positive infinity, then we can get that the limit point of the xk is the global minimizer of the original constraint problem. Okay, so this is a very nice property. However, in practice, if the problem of unconstrained quadratic penalty problem is not convex, it is usually difficult to get the exact global minimizer. Okay, therefore, we may only can get the local minimizer or stationary point. So the following theorem here actually mentions that when we only can solve the first order optimality condition of the inner problem, then the limit point of this sequence will also be the first order stationary point of the original problem. Okay, let's take a look at the details here. So we assume that the tolerance tau k tends to 0 and mu, the penalty parameter mu, tends to positive infinity. Then if a limit point x star of the sequence xk is infeasible, in this case, x star must be a stationary point of the quadratic norm of constraint Cx. Okay? This is one case. Another case is that if a limit point x star is feasible, and if the constraint gradients Cix star is linearly independent, then we can see that x star is a KKT point of the original constraint problem. For such point, we have the following result, that for any infinite subsequence k, that this small index k lies in the big K, where xk tends to x star, then we have that the limit point of mu k multiplied by Ci xk will be the Lagrange multipliers lambda I star for all this I in the equality constraints part. Okay? In other words, if x star is a feasible point, and LICQ holds, then we can see that X star is a KKT point, and we can also derive the corresponding Lagrange multiplier in this way. Okay, so which is actually a local convergence sequence result. Okay. Now, let's make a brief summary about this part. In this part, we introduce the quadratic penalty method as well as its global convergence result, okay, under different assumptions. One is under global optimizer solution. Another is that we assume the xk is just an approximate stationary point. Okay, we stop this part here and see you next time.